Alright, so let us now prove that if we are given a subspace W in an inner product space V which is finite dimensional, then V is the sum of W and its orthogonal complement. But because we have already proved that these two subspaces intersect trivially, that is, their intersection is the zero subspace. So once we prove this, it would imply that this sum is a direct sum. So let's see how that can be done. And in this proof, we are going to use the fact that every finite dimensional inner product space has an orthonormal basis, which we have already proved in the previous video. So the proof goes like this. Actually, there are two proofs given in the text, but we are let's go through the more algebraic one, and the analytic or geometric one is left to you, because clearly one proof suffices. Since W is the subspace, I am not exactly copying what is written in the, not the exact language that you find in the text, but it's the same thing. Since W is a subspace of the inner product space V, W is itself an inner product space. Its inner product is the one on V restricted to W. That just simply means that the inner product, that function which you have on V, if you restrict that to W, then the restriction also becomes an inner product on W. More specifically, that just means this. So an inner product on V is what? It's a function. We often denote it by this symbol, or if we are using angular brackets, by this, which just indicates the fact that there are two inputs, two vectors that go in these places, and as output we in general get a complex number. So the inner product on V is a function of this type. Now because W is a subspace of V, the Cartesian product W times W is a subset of this Cartesian product. So we can think of the restriction of this inner product function to this subset. And it can be verified quite easily that if this is an inner product on V, then this is also an inner product on W. That is, you have to verify the axioms, which can be done. Okay. And it's pretty straightforward to do so. So we are just simply mentioning that because of this, W is also an inner product space in its own right. Okay. But also it's given that V is not simply an inner product space but a finite dimensional one. So being a subspace, W is also finite dimensional, since, okay, I think it will be better to write moreover. since V is finite dimensional, so is W. That means now W is a finite dimensional inner product space. So it will have an orthonormal basis by our previous result. Hence, there exists an orthonormal set of vectors in W that is a basis of W. Okay. Let me complete the proof, because this is how it's given in the text, but after that we will see something a little, it's not anything major, but something about writing this set. Okay, after the proof is over, we are going to discuss about that. So fine, so this is one basis of W, which is also an orthonormal set. Now, for any vector in our original vector space V, we have seen that lemma, the lemma 445. The vector V naught, which is just this, V minus the inner product of V and W1 times W1 minus the inner product of V and W2 times W2 and so on, WR times WR. We have already seen in this lemma that regardless of what V is, this vector V naught, which we are calling V naught, is orthogonal to each of the vectors these. That means each of the basis vectors of W. This we have already seen in lemma 445. So that means what? It just simply means that if we consider these inner products, we are going to get 0 for all possible i's from 1 through r. But we know that since these vectors form a basis for capital W and these inner products are 0, so the inner product between V naught and any linear combination of these W's will also be 0, or in other words, that V naught will be orthogonal to every vector in capital W. Naturally, because the vectors in capital W are going to simply be linear combinations of these basis vectors. Thus, let's write that in symbols. V naught comma W is equal to 0 for all W belonging to W. But when that happens, what is it that we say? In that case, we say that V naught belongs to the orthogonal complement of W, because that is the definition of the orthogonal complement. This implies V naught belongs to this, the orthogonal complement of W. Now, our original vector V can be written like this, using this V naught. So, what is V from this equation? V is equal to this vector, by this vector I mean the one that you get after adding all these things on both sides. So, V will be equal to this. This vector means this linear combination plus and V naught. Now you can clearly see that since this is a linear combination of the Wi's, so this linear combination would belong to capital W, and V naught we just now seen it belongs to W orthogonal. So that means this sum belongs to W plus W orthogonal. So what have we shown just now? That any element V in V is also in this sum. Hence, V is contained in this sum, but of course the sum is also contained in V, since it's the sum of two subspaces of V, both of which are being subspaces, they are subsets of V. Or this, but we already know that this intersection is trivial. It's as small as such an intersection can get. Hence, the above sum is direct. I.e., if you want to use the symbol, you can also write like this. V is the direct sum of W and W orthogonal, where in place of ordinary sum we write O plus. O plus means we write the addition symbol and enclose it within a circle. This thing. Okay, so that's how we have our result. Now this result has a very nice corollary. The corollary is just this: if V is a finite dimensional I forgot to say, I said a little while ago that we are going to discuss something, no? I forgot that, but let me just complete the corollary. Let me just write the statement and then I will say that, what I was trying to say there. Inner product space and W is a subspace here, and W is a subspace of V, then the orthogonal complement of the orthogonal complement of W is nothing but W itself. Okay, so let us now go back to the proof we have just now seen before we prove this. So there what we did, we reasoned like this in the previous proof, no? That since W is a subspace of a finite dimensional inner product space, W itself is also a finite dimensional inner product space, and hence there is an orthonormal set of vectors. But there is a special case, which is this. W itself may be the zero subspace also, because that possibility is there. For this particular subspace, the basis is the empty set, and definitely the basis that we wrote, which is an orthonormal basis for W, in this case does not work. So that means what the proof we have of the previous result in the text actually considers this case, although it's not explicitly mentioned, as is the case with most of the proofs in this text. This kind of simple little things are usually ignored. However, let us see what happens in this case. In this case, if I am not going to go into the details, but it's very easy to see, you will see that W orthogonal, if W is the zero space, is nothing but V itself. Actually, it's very easy to see why that is so. That's because you take any vector from V that is going to be orthogonal to the zero vector, and that is why any vector in V belongs to the orthogonal complement of W, and as such the orthogonal complement is the entire vector space V. And in this case you can clearly see that V is equal to 0 plus V, or in other words W plus W orthogonal. So you need not go through that argument for this simple case, but once you have handled it, and you have seen that in this case also everything is according to what is being claimed, then you can then assume this condition and go on with the argument. In fact, that's what the text has done, although this has not been mentioned explicitly. I do not like this fact that Herstein keeps doing, but it's his choice. What can I do? We have to take care of these things. I also forgot to write that here, but now you can see it. Okay. So let's now see the proof of the corollary. Let me just keep it like this here itself. Let me not erase it immediately. And there is one more thing. Where have we used finite dimensionality in the previous proof? Namely, in the fact that there is an orthonormal basis. There we used the finite dimensionality. There is a finite orthonormal set of vectors that forms the basis. Here also we will need the finite dimensionality of the original space. Okay, so if V is finite dimensional inner product space and W is the subspace of V, then we have this. Okay. For any W in W, say W is any element in W. Now our aim is to show that this W belongs to the orthogonal complement of the orthogonal complement of W. To show that, what is it that we have to show? We have to show that W is orthogonal to every vector U in the orthogonal complement of W, because then by definition W will belong to the orthogonal complement of this, that is this. Let's see if that is true. So for any W in W, we have for all U belonging to W orthogonal. So here it seems like we have just simply written what we wanted to write here, what we wanted to show here. Is it true? Yes, it is true. Why? Because since U belongs to the orthogonal complement of W, U will be orthogonal to every vector coming from capital W. In particular, U will also be orthogonal to this particular vector. So that's why the inner product is 0. So now we can write what we wanted to write. So W belongs to this subspace, i.e. our original subspace W is a subspace of this. Okay. And now we are going to use finite dimensionality. Since V is finite dimensional, it follows from the previous theorem that W plus W orthogonal is equal to V. In order to indicate that this sum is a direct sum, we are using this symbol. But at the same time, we can write this same equation, the similar equation, for the subspace W orthogonal itself, because that is after all again a subspace of V. So that means V in place of V, we can also write this. Oh, and this sum is also direct sum. Now if we apply dimension throughout these equations, then what is it that we get? this is equal to dimension of V, and this is equal to dimension of this sum. Now note that we have direct sums, so the dimensions will just be the sum of the individual dimensions. Do not write direct sum here, okay, because these are ordinary integers, positive integers, well, non-negative integers. Just like that, this is also the sum of the dimensions of these two subspaces. But now, of course, you can cancel this dimension from both sides and have this. So you now have two things. W is a subspace of this subspace, and at the same time they have precisely the same dimension, and when that happens, the two subspaces actually have to be identical. Why? Because we have already proved that if you have a finite dimensional vector space and you have a subspace which is a proper subspace, then the dimension is smaller for the proper subspace. So if you have a relation like this, a containment relation, but the dimensions are equal, then this one cannot be a proper subspace of this. This one has to be, they two have to be identical. Hence, W must be equal to the orthogonal complement of its orthogonal complement, and that completes the proof. And that completes this section also. In the next vector space update, we are going to start solving the exercises that come after this. And then after this section is over, I mean when the exercises are over, we have that one section remaining, right, which is about modules. We will need to study modules because there is a result on finitely generated modules over Euclidean rings, okay, which help us in knowing the structure of finite abelian groups. So we will see that, we will see these things in the next vector space update. And tomorrow we have our usual upload, one more. So last week what we did, I am not able to remember. Maybe it's the case that last week last Saturday we solved exercises from Lee's algebra. If that is the case, then tomorrow we are going to solve group exercises from Gallian. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.